graph traversal algorithms, depth first and breadth first search algorithm. Both are examples for decrease and conquer. Here graph traversal means you are required to process all the vertices and edges of the graph in systematic fashion, because you already know that graph is a non-linear data structure, so you cannot process the vertices in sequential order. Some way of processing the vertices of the graph is required. One such algorithm I am going to discuss now is depth first search algorithm. In depth first search algorithm, the idea here is start with A, then visit adjacent to A, then adjacent to A, then adjacent to A is this. So depth first search. So here start with A, then B, then C, then D. With that you have reached a dead end. There are no more vertices to be visited. So now backtrack to C, then B, then visit E, again backtrack to A, then visit F, then G, then finally H. So now this whatever number I have written here will indicate the order in which the vertices are visited. That is A, B, C, D, then E, then F, G, H. Now we'll see the pseudocode for DFS. Here all the vertices initially you have to mark with value 0. That indicates that all the vertices are not being visited. Now use the count variable. It's a global variable initialized to 0. Then for each vertex V, in vertex set V, if V is marked with value 0, then you have to invoke DFS with that vertex V. Then increment the count by 1, mark V with count. For each vertex W adjacent to V, if W is marked with 0, then you have to invoke DFS with node W. Let me explain with the previous example only. So initialize all these vertices with value 0 initially. So then count is set to value 0. Call the first vertex as V. Now that is first vertex V is nothing but A. So invoke DFS with A. When you invoke, then increment the count by 1, mark V with count. Here V is nothing but A. Now A is set to 1. For each vertex W in vertex set V adjacent to V. So now adjacent to V is B. Initially all these are equal to 0. Since it is marked with value 0, invoke DFS with B. This is all about DFS algorithm. So let me explain again what DFS algorithm is. Initialize all the vertices as equal to 0. This indicates that all vertices are not visited. Mark each vertex in V with 0 as a mark of being unvisited. Then set the global variable count to value 0. For each vertex V in V, if V is marked with 0, call DFS algorithm with V. Then increment the count, mark V with count. For each vertex W adjacent to V, if W is marked with 0, call DFS algorithm. Here initialize all with value 0, then set the count equal to 0 for each vertex V, if it is marked with value 0, then invoke DFS and increment count by 1. So after incrementing count by 1, assign that count to V. Now here I have assigned 1 to V. Then for each vertex W adjacent to V, if W is marked with 0, here initially B was marked with value 0, then call DFS with node B. So again this count gets incremented, that incremented count value will be assigned to B. So like this the algorithm will work. Now we'll see for another example here. In this graph there are 10 vertices. Since we are following here lexicographic order, I start with A first. So in order to traverse this graph by applying DFS algorithm, we are using a data structure called stack. Now start with A. So since you are starting with A, push this A to stack, then C, then D. For A, all these three are, even though all these three are adjacent vertices, since I am following dictionary order, so I am considering C as the adjacent vertex. This A, C, D. So with that you have reached the dead end. So when you reach the dead end, pop out the top element from the stack. Now top element in the stack is D. So this is removed. Now on the top of the stack C is there. For C the adjacent is F. Then for F both E and B are adjacent, but since we are following dictionary order, I'll push B first into the stack and then E. With that again you have reached the dead end. Now pop out this E from the stack, then B, then F, then C, then A. So with that you have removed all the vertices of the graph from the stack. Now there are some more vertices which is marked with value 0. So freshly you have to start DFS algorithm with this G, because compared to G, H, I, J, J comes first, start with G. So count is a global variable, already its value is 6. So now since you are invoking the DFS algorithm with G, now G will be assigned with the count 7, then adjacent to G is H, then I, J. So 7, 8, 9, 10. This is the order in which the vertices are pushed into the stack. So with this you have reached the dead end, that is G, H, I, J. Now remove this from the stack. Now I will be on the top. Already you have explored all the vertices, adjacent vertices of I, so there are no more. So pop out this I, okay, then H, then G. So the popping of order for this graph is 7, 8, 9, 10. 7th one is J, then 8th one is I, then H is 9th, and G is 10th element which is popped out. Now when you traverse this graph, the order in which you are traversing, this order will redraw the tree. Will redraw the graph as tree like this: A, C, D. Then you will be backtracking to C. From C you are exploring F, B, E. Okay. Then firstly you started with G, H, I, J. So now you are getting two trees here. Both are disjoint trees. So a set of disjoint tree is called a forest. Whenever you apply DFS algorithm, if you get a forest then you can say the graph is disconnected graph. This is disconnected. You can easily make out by looking at the graph. So now here, when you traverse this graph, look at, this is a connected graph. You'll be getting a single tree. So when you get a single tree, when you apply a DFS traversal algorithm, then it is connected graph. Second property of the graph you can derive is whether the graph contains cycle or not. Here, look at here, you are getting a package, that is D to A, because there is a H from D to A, again there is a H from E to F, and there is a H from E to A. A H connects a node to its ancestor is called package here. So like that you are getting many packages. This indicates that graph contains cycle. So we have derived two properties when you apply the DFS algorithm. One property is you can derive whether graph is connected or not, or cyclic or not. When you get a forest, then you can say the graph is disconnected graph. If you get package, then you can say that graph is cyclic graph. When there is no package, then the graph is not cyclic. It is a cyclic graph. Okay, these properties can be derived when you apply DFS traversal algorithm. So DFS algorithm can be implemented with the graphs represented as adjacency matrix or adjacency list. If you have implemented graph using adjacency matrix, then DFS algorithm complexity is theta of v square. If it is implemented using adjacency list, its complexity is theta of modulus of v plus modulus of e. This DFS yields two distinct ordering of vertices. One is order in which vertices are first encountered, that is pushed onto the stack. Second order is order in which vertices become dead ends, that is popped off stack. As I told you when I have with the example, you can check whether the graph is connected or not, or you can find connected components. You can check the acyclicity of the graph, and you can find the articulation point. And also by applying DFS algorithm, you can construct state space tree to find the solution for a given graph. In this example, this is called articulation point because removal of this point results in disjoint components of the tree. So that's why it is called articulation point.